Hi students. As you know, when an electrical engineer designs a power transmission system, he needs to consider the commercial aspect also. When it comes to the economics of power transmission, we need to consider the economic choice of conductor size and economic choice of operating voltage. In this class, we'll see the economic choice of conductor size. That is, how we can choose the most economic size of area of cross section of the conductor using Kelvin's law. In the economics of power transmission, we need to consider the economic choice of conductor size as well as the economic choice of voltage. In this class, we'll see how we can choose the most economic size of conductor. The most economical area of the conductor is that for which the total annual cost of the transmission system is minimum. Annual cost of transmission line includes the annual charge on the capital outlay. This is due to the interest and depreciation, and the annual cost of energy wasted in the transmission line. This is due to the heat loss in the transmission line. The annual charge on the capital outlay is due to the interest and the depreciation of the cost of the conductors, then the cost of supporting structures, then the cost of insulators, then the cost of erection, which includes the wages of the people working with the system. This annual charge, a part of this annual charge is fixed and a part depends on the area of cross section of the conductor. The cost of conductors depends on the area of cross section of the conductor. The cost of supports and the cost of erection. A part is fixed and a part depends on the area of cross section. The cost of insulators, it doesn't depend on the conductor size, rather it depends on the operating voltage. So we can write the annual charge equals P1 plus P2 into A. A is the area of cross section, P1 and P2 are constants. So a part of the annual charge is fixed and a part depends on area of cross section of the conductor. Now we will see the annual cost of energy wasted. The energy wasted in the transmission line is I square RT. As you know, the resistance is inversely proportional to area of cross section of the conductor. So the annual cost of energy wasted in the line is equal to P3 divided by A. A is the area of cross section and P3 is a constant. Because energy wasted is inversely proportional to the area of cross section of the conductor. The total annual cost C is equal to P1 plus P2 into A plus P3 by A. P1 plus P2 into A is the annual charge and P3 by A is the cost due to the energy loss in the line per year. In order to find the minimum cost, we need to differentiate this expression with the variable A and equate it to 0. So dC by dA should be equal to 0, or d by dA of P1 plus P2 into A plus P3 by A should be equal to 0. the differential of P1 is 0, differential of P2A is P2, differential of P3 by A is minus P3 divided by A square. This should be equal to 0. Or we can write P2A equals P3 by A. This is the variable part of the annual charge. This is the cost due to the energy loss in the line. So we can write variable part of annual charge equals the cost of energy wasted per year in the transmission line. So this is the condition to find the most economic size of the conductor. So the Kelvin's law says the most economic area of the conductor is that for which the variable part of annual charge equals the cost of energy loss per year. We'll see the graphical illustration of this Kelvin's law. As you know, C is equal to P1 plus P2 into A plus P3 by A. In the y-axis we have the cost, in the x-axis we have the variable A, area of cross-section of the conductor. First, let me plot this P2 into A. Is the straight line passing through the origin. This is P2 into A. Now let me plot this P1. It is constant. This is P1. Let's add these two curves. So this is P1 plus P2 into A. P1 plus P2A. So P2A is shifted up by an amount P1. Now let's plot P3 by A. This is P3 by A. Now let's find out P1 plus P2A plus P3 by A. So this is P1 plus P2 into A plus P3 by A. In this graph you can see this is the minimum cost of operation. So this is the minimum cost line. In the minimum cost line you can see P2A equals P3 by A. What is this P2A? It is the variable part of annual charge, and this P3 by A is the cost of energy waste in the transmission line. So at minimum cost operation, these two should be equal. When this condition is satisfied, we get the most economic size of conductor. So the Kelvin's law says that in order to find the most economic size of the conductor, the variable part of annual charge should be equal to the cost of energy loss per year.